Alright, we're picking back up in section 5 of chapter 7. We were just talking about finding the angle between two vectors if the vectors are written in standard position or shown in standard position. And we had this formula here, and we talked about this in the last video. We also did an example, but I wanted to emphasize here that the denominator, or magnitudes, they're principal square roots, and you're multiplying two positive numbers together. The denominator is always positive. The numerator is going to be positive, of course, if the dot product is greater than 0. Now, if the dot product is greater than 0, I have a positive expression. That means the cosine of the angle is going to be greater than 0, and that means you have to have a first quadrant angle. On the other hand, if you are looking at a dot product that's negative, that means the whole expression is negative, and when you take the inverse cosine, you're going to get an obtuse angle, an angle between 90 and 180, including the 180. Now, if the dot product is 0, if you have a 0 in the numerator, all over a positive number, 0 over positive number is 0, and that means that the cosine of what angle is 0, well, that would be 90 degrees. That tells me that if the dot product is 0, the angle between the two vectors is 90 degrees. We say that the vectors are perpendicular, although we don't really use the term perpendicular out when we're talking about vectors. We use the term orthogonal, and I mentioned that in the other video. Orthogonal vectors are two vectors, v and w, vector v and vector w are orthogonal if and only if their dot product is equal to 0. Now, what does it mean for perpendicular? What does it mean for orthogonal? What does it mean for normal? Normal is another expression. Perpendicular typically is talking about lines. Orthogonal is typically talking about vectors. They all mean that they form 90-degree angles, and normal typically has to do with a plane and a vector, or a plane and a line. So you're going to be seeing both of these, not so much this guy, seeing both of these in this last section. But remember what it applies to. Perpendicular, you're talking about lines. Orthogonal, you're talking about vectors. But they mean they form 90-degree angles. So let's determine if the vectors are orthogonal, which means see if the dot product is 0. Well, I have these two vectors written in terms of the unit vectors, vector I and vector j. I'm going to write this one as 4, 3, and I'm going to write this one as 6, negative 10. Now, if the dot product is 0, my answer is yes, they're orthogonal. Well, that would be 4 times 6 plus 3 times negative 10. Doesn't look like it. It looks like I have 24 minus 30, which is negative 6. So the answer is no. Okay, by the way, I noticed that some of you use like a check mark for yes and an X for no. Just write down the words. Yes and no, please. You can put the check mark in the X if you want to, but then write down yes or no as well. Down here, I want to see if vector S is perpendicular or orthogonal. I should say almost I did it, to vector T. So I'm going to take negative 2, that's a 2 there, not a Z. Negative 2, 1. And I'm going to take the dot product with, it looks like 11, 22. So I have negative 2 times 11 plus 1 times 22. Yeah, I think this is going to work. This is going to be negative 22 plus 22. This is 0. So, yes, the two vectors are orthogonal. Now, I'm working my way to being able to do some application problems besides finding the angle, besides showing that two vectors are perpendicular or orthogonal, I should say. We want to get to a point where we can do some actual applications, as my diagram over here to the right trying to show there. Two vectors, I'm sorry, almost jumped the gun. Two vectors, v and w, are parallel if one is a scalar multiple of the other for some real number c. So, if you have, for example, vector 3, 3, and you have vector 6, 6. Okay? These are indeed parallel to one another because you can multiply this vector by a scalar to get the other vector. Now, parallel in terms of vectors has to do with either they're going in the same direction or they're going in opposite directions. If the dot product equals the product of their magnitudes, I'm going to explain that in just a second, or it equals the opposite of the product of their magnitudes, then we have parallel vectors. All right, so what this has to say is, if you have this expression here, that would be the product of their magnitudes, and you have the dot product up here, right? If I get 1 or negative 1, that would mean that their dot product was either equal to the product of their magnitudes, or if I get negative 1, the dot product, when does that happen? When does the cosine equal 1? When does the cosine equal negative 1? Well, you're talking about at 0 and at 180. So what we'll have there are vectors that are parallel. They're either going in the same direction or they're going in opposite directions. It's kind of maybe difficult for you to picture. I think it's a little bit easier if you remember it this way. At least that's the way I've always remembered it when I had to talk about vectors that are parallel to one another. Now, here we go. In some applications, it's important to find what's called the contribution of a vector in a particular direction. The contribution is what we're going to talk about here in this. What does it add to the vector? Consider a car parked on a hill with an angle of inclination at theta. The force of gravity, F, which is this one in the black ink here, you can see that, pulls straight downward. Vector F can be, quote, broken down or decomposed into forces F sub 1 and F sub 2 that are acting parallel to the hill and acting orthogonal to the hill. Now, that's supposed to be purple down here, this little guy. He's supposed to be parallel to the hill, and the pink one here is supposed to be perpendicular to the hill. Not to the ground, but to the hill. The gravity is perpendicular to the ground. And as you can see here, this force, F sub 1, is the sum of these two vectors, F sub 2 and F sub 1. This force right here. F sub 2 and F sub 1 are called the vector components of F. Okay, let's run through that again. They're called the vector components of F. This is going to come into play. Okay? Now it says the vector components of vector F are important because in this case they determine the opposing forces needed to keep this car from moving. The vector, the opposite of F sub 1, that'd be this way going this direction, is the minimum amount of force needed to keep the car from rolling down the hill. Gives you some appreciation for the emergency brake. The force F sub 2 tells us the amount of force that the tire must withstand upon the ground. As the car is being pulled down by gravity, it's putting pressure from the weight of the vehicle onto the tire, which is why you want to keep your tires in good condition. Now what we're going to do is we're going to see how we can use vector components in some application problems, and that's on the next video.